We just saw how a simple linear model is not powerful enough to solve the XOR problem, a classifier that really only has four possible outputs. If the four possible inputs and two outputs. If the two inputs are the same, 0, 0, 1, 1, output one value. If they're different, output another. And linear models can't solve this. And you can get intuition for that by looking at what the space is of these input and output pairings, and then realizing that a line through that space is simply not going to cut it. So how do we bring more power to this simple linear model? Well, we have one idea, which is these nonlinearities, but here's another idea. Let's explore that one first. What if we just add more parameters to the model? Okay, so here's our initial model. I've rewritten this a little bit. I've redrawn this a little bit to be more compact, so we're going to add some stuff here in a minute. So here I am again, 1, x1, x2. That's my input. Here are my model parameters, w01, w11, w21 with a superscript 1. Notice that I've added a whole bunch of stuff here, by the way, in terms of the indexing. I'll come back to that in a minute. And so this is the same as before. Multiply these inputs by weight, sum them up, which I have here, and then get an output. No nonlinearity. So this is a linear model. We know this won't cut it. Well, what if I add a little more power to this? What if I add another set of weights? So notice what I've done here now is I've now have W01, W02 associated with the 1. W1, 1, 1, 2 associated with the 1. So the first subscript tells me what my input is, and the second is we're going to multiply it by a different number. And same thing down here. And so I take the first set of weights, W01, W11, W21. I multiply by the inputs, and I sum them up here. And then I get a whole nother set of weights, and I multiply that by the input, and I sum them up here. Now I have two things coming out. What do I do with those? Well, let's weight those all over again. So let's drag the 1 over here because we want the constant. And now we have the superscript corresponds to which level or layer we're in. Now you're starting to see the combination of these neurons. One layer of neurons here, another layer of neurons here. We have two sets of weights here because we're gonna do two calculations separately, and then we're gonna bring them all together with the same linearity, and then we get an output. So surely there's more power here. I went from 3 weights to what? 3, 6, 9 weights. And that seems like, sure, you've added a lot of complexity, but surely I have more computational muscle here. I also have more work to do because I have to learn all of these weights. Well, let's see what the consequence of doing all of this is in terms of our mathematical power or our discriminatory power. So let's write this out. This is going to be a little tedious algebraically, but it's really important to see this for a very simple idea. This y hat here is equal to what? All right, it's equal to W12 times W22, that's these two weights right here, times a whole bunch of stuff, which I'll come back to, plus this constant term. So these two weights here with the subscript 2, and this weight here with the superscript 2, rather, correspond to this layer in the network. All right, what's inside of all of that? Well, it's x1 and x2 from over here being multiplied by their weights, which I've put into a matrix. So in the first row of this matrix are the first set of the weights, and in the second row are the second, and then I have the constant terms here. I realize there's a lot of notation here, but I'm just rewriting all of the weights here into matrix form. So in the first step, I take x1 and x2, I scale them, and then I add something to it. I take the output of those, and I scale them again and add another constant. Okay? And it seems like I have a lot more computation here. Well, let's see what actually happens when we start breaking this down. So again, x1 and x2 are the inputs. The first row of this matrix corresponds to these two here, and then this constant term corresponds to that. Good. And then I've got this weight corresponding to that. I've got this weight corresponding to the constant over here, and that's going to give me the first entry into that final summation to give me my output. Now, same thing happens all over again. I've got the same input. I've now got these 3 weights in the second set of neurons, and I'm going to multiply and add that to their constant. I'm going to take the output of that, multiply it by that constant right there, and then add that same W02, and all of that gets summed up to give me an output. All right, what is the consequence of that in terms of numerical power? Well, let's see. Let me write out this matrix right here. So this is the first row times this column plus that entry right there, which is this thing right here. Yeah. And the next element is this row times this column plus that constant, which gives me this. And then I'm going to, of course, multiply that by the first element in this vector is going to get multiplied by that. The second element is going to get multiplied by that. And then I'm going to add that to this final value here. So my final output is what? W12 times a whole bunch of stuff that have to do with x1 and x2 plus W22 times a whole bunch of stuff plus W02. Let me just rewrite that as what? It's W1 tilde times x1 plus W2 tilde times x2. Why? Because I'm just taking linear combinations of x1 and x2 here, and I'm not doing anything new. So let's make sure we see that. Here is a weight times x1. Here is a weight times x2. Here is a constant term. Here is something times x1. Here is something times x2, and a constant and a constant. So I can bundle all those terms together. I can bundle up everything that multiplies x1, everything that multiplies x2, and then some constant. And what am I left with? I'm left with a linear model and 3 unknowns. So after all that work, I added 9 parameters. I added 2 sets of neurons here. I added 2 layers. And after all those calculations, I ended up with a single linear layer with a single neuron. Combining multiple linear transformations is a linear transformation. And so there is no added power in this machinery that we just created, which is both a little surprising and a little disappointing. But then when you go back to when you think about it, well, everything is linear to begin with, and linearity on top of linearity on top of linearity, there's nothing new here. Nothing changes. And so by simply adding neurons, multiple things happening to the input, and layers, putting them more and more calculations, there is no gain to be had, and we still can't solve XOR. So where is the power? It's in that nonlinearity, and we'll come back to that when we come back.